So this is the second half of this NARS introduction. Last week, I gave an introduction for the logic part, and today we will talk about the control part. Again, it's not about all the details, but more about the ideas behind it and why it's designed in this way, the big picture. So in general, we can say a reasoning system is designed in 2 or 3 layers, depending on how you count. Okay, here I would just say that first we need to decide a representation language, typically a formal language. In our situation is the NARS. And this language will decide what can be expressed within the system. So it's kind of like the system's overall limit. If something cannot even be said, of course, there is no way for you to process it. At least not directly. Then that is mostly done. And then on top of that language, you need to have a bunch of inference rules when we are talking about reasoning system. For our case, that's the non-axiomatic logic for now. And that part will decide what can be derived in each individual steps. And these 2 parts put together, you can call it the logic part of the system. That's what I covered last week. And then to really make it run, you need another part, which is usually called the control part or control mechanism, to really finish a complete reasoning system. In our situation is NARS. Okay. And this one will decide how to organize the steps provided by each individual rule into a complete process for each problem to be solved or task to be processed. Another way to see it, as I usually say, is the logic part decide the possibility. That is, what is possible, what is impossible in this system. And the control part selectively realize some possibilities. There is no way for you to realize all of them because of this and that restriction. But some of them. So that selection is actually the job of the control mechanism. To be specific, we can see inference as task processing. Task is something you want to do in general. Each narcissist sentence actually, as soon as you put it into the system, it will be treated as a task to be processed. There are 3 types. What we call judgment is a piece of new knowledge you put into the system, or it's a statement with a truth value. Goal is a statement you want it to be true. So there is no truth value, but instead you have a desire value associated to indicate how strongly you want it to be true. And question is just a literal meaning. You ask the system question, typically is about the truth value of a judgment or desire value of a goal. So question can be further divided into 2 subtypes. So that's what the system can accept as a task. On the other hand, we distinguish task from knowledge. And the knowledge is kind of like, the background knowledge or the data or the information have been collected to process the task. Furthermore, you see previously in my early publications, I sometimes just distinguish, use knowledge and beliefs in the same way, just because in NARS, usually they're the same way. But now I make a further distinction. I use knowledge as a more general term. And beside it, I further distinguish beliefs and desires. Beliefs, you see, is a summary of the judgment from experience. Again, is a statement with a truth value. Desires, on the other hand, summarize the goals from the experience. So it has a desire value. So put both of them together can be called the system's knowledge, which is nothing but a summary of the system's experience overall. So in each inference step or each inference process, Each task is eventually achieved to a certain level using some of the system's knowledge. And in this process, the system will recursively derive new tasks and new knowledge, and so on. So that's what is called reasoning or inference in a system. That's kind of like simple. So now we really move into the design of the control part. So what I just said basically can be applied to all reasoning systems, even though they may use different terminology. Okay, what makes our situation special? Of course, you all know is the assumption of insufficient knowledge and resource, AIKR or acre. To be specific in this situation, as far as control is concerned, it has the following property which make it different from almost everyone else. One is multiple tasks at the same time. Some of them are directly come from outside, and most of them actually is derived by the system itself. And that is not normal. The normal part is they may conflict in two aspects. One is in what they want to do. They may have actually goals which are not compatible, and also they compete for resources. That's for sure. And that's one. That's the insufficient resource part. Insufficient knowledge part in this aspect is you don't have a algorithm for each task. Well, not for all of them. For some of them, you know how to do. But very often you run into a task, you just have no idea how to achieve it. And also, you see, I say no affordable algorithm, because in this context, if you just say, oh, try all possibility, exhaustive search, that's not acceptable, right, for this resource restriction reason. And also, it's a real-time system, meaning that it requires fast responses. So that's the challenge. Under this challenge is already, by definition, we see that there's no way for you to solve all of the tasks perfectly just because you don't know or you don't have the time. So the solution or the answer or NARS take for this situation is summarized in this keyword adaptation. First, it does not aim at a certain quality or optimal solution for each individual task. Instead, it aims at the overall achieving level of the tasks. Okay, so it tries to achieve some kind of balance or overall or total achieving. Okay, which means it will have to handle conflicts and contradiction and so on somehow. And for each task, if it doesn't know how to solve it, then what? Well, it will try to explore that available or the paths that can be discovered from the system's knowledge and try the promising ones, which also follows to the system have to dynamically reallocate or distribute its resources among the possibilities. Here, the keyword one is distribution or allocation. Another one is dynamic because the system, the situation or the evaluation change over time. So you cannot really plan everything at once as in many AI systems. So you see, each inference step, and that's basically what we covered last week, right? Each inference step is carried out by one or very often more than one inference steps, but for each inference rules, and each rule each time will take a task and a belief. When I say belief, sometimes actually it means desire. I'm not going to distinguish them very clearly in the following, just to make the description simple. Okay, so anyway, task is what you want to process. The belief or desire is what you can use to process it. So almost always take a pair of them as the input. Here, input is not the input for the whole system. but the input for the inference engine, if you say there is an inference engine, or the inference rules. Or using logical term is we're using this tool as a premises in the inference rule. Then this pair, their combination will decide which rule is applicable, which is also something I covered last week. Okay, so you can see it's a little bit like data driven. You don't decide, I want to do induction, then do abduction. You feed the data to the inference engine, and their combination will trigger whatever available rule. Then you're going to get new task and new belief derivative. Then also this result will provide feedback to the input items, that is the task you're processing and the belief you just used. And each inference step is a basic unit of the scheduling in the sense that it cannot be interrupted. Okay. But also it's designed in such a way that it has a very relatively small constant time and state cost. Then an inference process is just a combination of those steps or a sequence of those steps. Here, the key is, in principle, an inference process can consist of any number of inference steps, which means that how deep or how far a task will be processed is not predetermined. Actually, the extreme situation is the number of steps can be 0, which means a task may be completely ignored by the system. It can be 1, it can be 2, it can be 3, it can be anything. That's also another way to say that we don't have a predetermined algorithm at the task processing level. Instead, you can say each step itself is an algorithm, that's for sure. So that means the process itself can be interrupted and terminated at any moment. So in that sense, it's have some similarity with the so-called anytime algorithm. So now, given that setup, what is the control problem? The control problem is nothing but selection. Okay. So a typical inference step means that you need to select a task and select a belief. After that, everything else will be decided by this tool. So you don't need to select anything anymore or control anything. So what's the restriction from this? Well, the tool must be related either semantically by sharing a common term. This is nicely or elegantly provided by a term logic mechanism, okay, which is used in NARS, I mentioned last time. Or this tool can be related temporally, or especially this is more for the perception part in the system's experience. Okay, so the system never tried to search the whole, say, knowledge space to looking for anything. That's very important, and also a key difference between NARS and many other reasoning systems. So who can reason with whom? That's already decided in the storage structure in a sense. Okay, they must be stored together, either in a common concept or later we will see in the same buffer. Okay, so the concept will provide a semantic relation, and the buffer will provide temporal and spatial relation. Okay, otherwise they will not be used together. So the mechanism of control is what I call in my early literatures, I call controlled concurrency. Okay, the idea is from operating system, which I mentioned several times. It's from that idea of time sharing, where everyone are familiar with. Okay, so time sharing means that I can process several things in parallel, but this is just conceptually, right? In reality, in hardware, I can still do that with a single processor by just switch between the processes. So that's the basic idea of time sharing, which I borrowed into this system so that we can process multiple tasks at the same time, conceptually speaking, even with a single core hardware. But of course, if you have multi-core, you can really do something more than that. But conceptually, they will be the same. It just the processing of tasks overlap in time. That's what parallel means in this context. It's not just you finish one, then you switch to another. But what makes it different from operating system is that first, the task will be processed with different speed. And that, in a sense, is also there in operating system because they have a different priority for different tasks, right? But in NARS, we are moving further. It's many very different levels of priority or speed. The second one is more fundamental. That is dips. That is, we do not process everything to its logical end. In operating system, time sharing, still, even if you have priority, which only decide who will finish first, who finish later, you still want to finish everything, right? Even if you have interruption, you pause a process. Normally, you want to finish it, unless you have explicit demand to cut or to kill a process. But in NARS, that's the kind of like opposite. Normal process will be terminated before they run into their logical end. You see, what is the logical end of a reasoning process? Is that a task has been processed by all relevant belief, as I said before, either in the same concept or in the same buffer. Okay, that's the logical end. I have nothing else to say about this task. But most of the case, and except at the very beginning when the memory doesn't contain much content, you never have that situation. So almost all the tasks will be terminated somewhere in the middle. So that's what I mean by dips. So you distribute your resource, not only decide which task will be finished first, they also decide how deep or how completely a task will be processed. So some of them, well, actually most of them will only be processed very, very shallowly, say, using a few cycles, and some of them will have, say, hundreds of cycles allocated to it. Okay, so that makes it very different in terms of behavior from operating system, even though the idea of time sharing are the same. So that's why I call it controlled concurrency. Here, concurrency just means parallel processing, right? Controlled means that I can change the speed, I can decide when to stop. So the candidates in this case, they can be task, they can be belief, they can be desire, whatever. They're all prioritized because there is no guarantee that each of them will be used or processed at all. So they need to compete for resources. So all of them are prioritized. How is the priority decided? Well, that's something complicated, right? So in general, we can just say that this priority is always decided according to multiple factors. It's almost never a single factor. Then later we will say that we have budget function to calculate the priority and so on. Okay. So now we use repeated probabilistic selection biased by priority to carry out the distribution. As I said, for example, if we only have 3 tasks at the moment, okay, I want the one to use 10% of my time, the second one use 20%, and the last one use 70% of my time. How can I do that? So again, it's time sharing, but with different access frequency. So I can use a random number generator, or actually it's a pseudo random number generator, to generate a probability distribution where there's A, B, C access with different probability. Okay, so here the key is to suggest this probabilistic mechanism is merely used to generate this uneven resource allocation. Is not introduced to create uncertainty. Many people have the feeling that creativity comes from randomness and the NARS uncertainty comes from its probabilistic distribution. That's not true. If you really check the code, you will see everything is fully deterministic, right? Even this random number generator is nothing but a predetermined distribution. Okay, we just describe it in this way to make it more understandable. So this so-called randomness or probabilistic mechanism is actually a way to distribute resource by changing that into repeated access, and each of them take the same amount of time. But since it's repeated biased by priority, then overall in the long run, you get a certain probability resource allocation. Here, repeated is the keyword, okay? If each task is only processed once, then it doesn't make sense to do this kind of probabilistic selection. It's only when they're repeatedly processed, then the probability will eventually become their processing speed or dips. So that's an important part. So we designed a special data structure called bag, which is a probabilistic priority queue, right, which have been described in many places. So each item in this bag can be accessed either with a key value or with a priority value. Okay. And the data structure is nothing but an array indexed by priority levels. And priority value itself is a real number, but in reality, of course, we just divided into different levels in this example. It's just 100 level, so that a similar priority will be put into the same level. So the accuracy here doesn't really matter too much. We use 100 usually is enough. Same level items are just nothing but put into a queue, first in, first out. Or a stack will not change too much. Then we also have a separate hash map, which provide access by key value. Okay. And that is independent to the priority value. And then another thing important is this whole thing has a constant capacity. Okay, how many items it can hold is predetermined by a system parameter. So the major operation, there are three major operations. Put an item in to the system, which means put both in the sense of a hash table and this prioritized linked list. And what makes it different from other data structure is there is underflow mechanism. That is, if this is already full, in reality, most of the bag are already full, just because the system keep adding things into it. Okay, no matter what's the capacity, eventually it will reach it. Then each time you put something in, new into it, the one with the lowest priority will be simply removed from the bag. Okay, so it's a form of absolute forgetting. And then there is a get operation, which is just exactly the same as get operation in hash table that's accessed by a key. So you can take it out of the table. What makes this one different from the others is the select, or sometimes we use a different term, but it doesn't really matter. Select by priority. That's the mechanism I mentioned before. So if you say select, you do not use any parameter, you do not say which one, okay? The bag will give you one, and which is, everyone is possible in principle, but high priority one will have high probability to be accessed. So that's why it's called a probabilistic priority queue. Okay, it's not always pick the top atom, or just kind of like pick the top atom, then pick somewhere in the middle, then the second top one again, and someone bottom, and then again and again, right? We actually have some sort of random number generator to control the relative frequency for each level to be accessed, which is positively correlated with the priority value. So this is a picture I already showed last time. Now we see it from the control point of view. Okay, the memory of the system is nothing but a concept network where each concept is a node and identified by a term. So here, the object we mean an object within the system is named by a term. Each of them will refers or stores relevant task and knowledge, meaning that this task and knowledge must contain the term itself. And the task and knowledge are both stored using bags, in separate bags, conceptually speaking. So each time you just say select a task, then you will get one based on the priority distribution. The same thing for knowledge. Okay, so in each step, in the long run, which task and which knowledge you're going to use concept is non-deterministic in the sense that we use that bag mechanism. But still there's some regularity as shown by their priority values. So this is what where what we call semantic inference happens. Well, actually, in a sense, all the inference is semantic. Here we just address that the task and belief are related by their common content. That is a common term. So the memory as a whole is nothing but a bag of concepts, which means that at a certain moment, some concepts will be more active than some others. Actually, most of them will be completely dormant. Just a few of them will be active. And each concept you'll see that is not a symbol like in traditional symbolic AI. It may correspond to a word in natural language, may correspond to an image provided by the sensory motor, may correspond to nothing outside. It's purely an internal identifier. But its meaning is determined by its relationship with the others. So eventually, everything's meaning will be decided by the system's experience. But there are different levels of abstraction. So some of them are directly related to experience. Some of them is kind of like more inside, so it's only indirectly related to experience, and so on. So that's the memory structure. Then buffer and channel, that's the new stuff we introduced in the new architecture. Okay, the memory structure has been there from the very beginning of NARS. Okay, so basically a concept network idea with priority defined. So the new stuff, there was a buffer before, but this new buffer is more complicated. It's a bag we defined before. So it's also a mechanism which have limited capacity and also support prioritized processing. Okay. What makes it different from ordinary bag is there is a timestamp items in it, and also each item can only stay within it for a certain period of time. Okay, that period, of course, it's adjustable. It's for now it's just a system parameter. Okay. So this is clearly a form of short-term memory. But it's not only a short-term memory. At the same time, it's also a working space, which provide temporal composition, which means, for example, if A is followed by B, then we're going to perceive AB as a whole, as a compound. At the same time, we're going to build the relationship between A and B. So in the future, if the system see A again, it will expect B to happen. Okay. I call it advanced, which I will explain later why. Anyway, in the current architecture, we have two concrete instances of buffer alone. One is called internal experience buffer. One is called overall experience buffer. You will see in the next slide in the diagram. Then another thing we introduced in this new architecture is what we call a channel. A channel is a buffer. A buffer is a band, okay, with this additional restriction, this temporal property. A channel is a buffer with additional property, which correspond to certain input-output operations, specially designed for a certain type of device. For example, we have a channel to connect it to a video camera, maybe another channel connected to a microphone, something like that. So each outside device is hooked to NARS through a channel, which contains a buffer within, so it already provides some, you'll see, primary temporal composition. As I said before, here, this one is a primary in the sense that they only work on signals coming from the same channel, meaning the same type of sensory or motor information. For example, all the pixels are initially processed here. This one I call advanced because at this level, we already may have information from multiple channels combined together, as you will see in the next architecture. So this is the new architecture we implemented in the most recent OpenNARS 3.1.0, which was finished in last summer by Patrick, Peter, and Xiang. So see, this is the picture that we have multiple channels. Each of them communicate with some outside stuff, outside device or system, which can have several different types. The most traditional one, this is what we have had all the time. That is a NARS channel. That is, you talk with the system using its own formal language. Okay, it can be both input and output. And this is what we call knowledge channel, is the one that we tried to connect NARS with some knowledge base, like concept net and word net, that kind of thing. Okay. And then this is a sensory motor channel I mentioned that it can be connected to vision and action and robot and so on. And each of them, of course, I draw one, actually there is a type or a group of them. And within each channel, maybe there's also several levels of processing. Okay, in this picture, we just ignore all that kind of details. And the result, the primary result of this will be all feed into what we call overall experience buffer. And this is a buffer, all the informations will be combined together. For example, if you see a picture and you hear a voice at the same time, and this tool will be integrated, combined in this buffer. And then you'll see as a buffer, it only selectively feeds things to the next level. So some of them will be ignored or filtered out here. Some others, more significant one, will be passed to the overall experience. And the overall experience will pass something to memory. This is the concept network I showed before. And then semantic reasoning will happen in the memory in the sense that we'll pick a task and believe and pass it to the inference engine, which actually only exists as a concept. Okay. Anyway, the task and belief will interact with each other. And then those immediate results will go into an internal experience buffer first. Okay. Again, here it's a filter, so we are going to ignore a lot of the result directly from the inference engine. If you have tried NARS, you will see that in each inference cycle, very often it produces a whole bunch of stuff. Okay, that's what I said. The inference engine is the logic part. is only responsible for the possibilities. Okay, so you give me two, I will give you all the possible outcomes, but it doesn't mean all the possible outcomes will be useful for you. Okay, so which one is useful? That's the job or the responsibility of the control mechanism to decide, according to the current situation, according to the past experience, and so on. Okay, so most of the possibilities will be ignored, will be thrown away. Okay, that's, you can think it as a waste, but I don't think there is a way for you to know which one will be useful, because you don't have an algorithm. Okay, so you don't know for sure about the future. So we generate them and allow them to compete in several different places. Initially, it will be the internal experience. And then you'll see that this internal experience and the external experience will also be merged or combined in the overall experience. And this will also give us a lot of interesting phenomena. For example, whenever you feel something and when you see something, and those two things may form some kind of, initially some kind of correlation in the system, okay? Which sometimes may eventually be interpreted as a causation. And by the way, on this Tuesday, we had an interesting discussion about causal inference in this 3 university seminar. So if you haven't listened to it, you may want to take a look. It's an interesting discussion. Anyway, then this something will go back. So as soon as you start the system, you'll see that it will run in this cycle at the same time. I will get input from the outside, each channel with a certain frequency, communicate with the outside world, and so on. So that's the big picture we realized in this new 3.1.0. For those of you who know the previous architecture, the memory part is the same, the inference part is basically the same, and everything else, there is basically one single buffer, okay, to do everything. Of course, with some additional addition later, like event bank and so on, but it's not very clear. Now I think we have a more clear picture about the whole thing. Of course, this is very rough, and there are a lot of details. But this is, I think, enough for you to understand the overall working process, especially for the new members. I hope this makes you feel a little bit better about how the system runs. So the new version, we all know, is finished, but they have a lot of problems to be fixed because of the new architecture. Demand a lot of change, which has not been finished within in the last summer. So to me, to fully address the control mechanism, include the following aspects. First, we still need to decide what kind of measurement we will need within the system, or what kind of factor should be taken into consideration. Now we have several levels. One is on each individual data item. For example, for each task, each belief, each concept, we currently have what? We have a priority value, right? We have a budget which include priority and something else like durability and quality and so on. And also for beliefs, we also have truth value, which of course also matters. Then there are other things, for example, the complexity, or the opposite, simplicity, is also a very important factor in this control mechanism. Then on the data structure level, like a bag and buffer and the channel, and also we can say a concept is also a data structure. So for each of them, we also have some measurement defined on them, which will be taken into consideration when resource allocation is concerned. And also on the whole system level, this is new. We don't have this, okay? In the new architecture, now we define some kind of like a global measurement about the overall satisfaction and whether the situation is perceived as a new situation or a familiar situation. and whether the system is busy with the existing task or it have free time to explore new possibilities and so on. So each of them is a measurement which are closely related to things like the system's emotion status and overall attitude and so on. Okay. So now the question still unclear is whether the current measurements are enough, or some of them are not really relevant, just make things more complicated than necessary, or some of them may later turn out to be redundant. They can actually be replaced by something else. We don't know. We have a bunch of stuff there. Each of them, of course, we have some justification why we want this one. But this need further work. And also, this is kind of like, you can also think control as systems interaction with its internal environment. So this is more like the perception part. Okay, you need to know yourself. Yeah, sense. And this is more like the action part. Then what you can do if you already know the current situation. Okay. Then I think I can further divide it into, first is the control process. The control process itself can be further divided into two parts. This is well known in psychology, okay? The so-called dual process system. There is an automatic control mechanism, which is kind of like a free association. Okay? Your attention will naturally flow without your explicit control from one place to another. This is carried out by the budget functions, which will use the information we perceived about ourselves to decide the priority, the new priority value and so on. Okay, for example, some tasks will be perceived as more important. Some will be less important. Some belief will be perceived as useful, so will be used more often in the future. Some of them is relatively forgotten and so on. And you don't need to think about this. This is built into yourself. Okay, so that's the budget function. Currently, we have all the budget functions, but still need a lot of tuning and revising and justification and so on. And then, but this is not enough, especially for complicated tasks. That is why currently NARS cannot really handle complicated tasks, because for complicated tasks, you always need self-control. You cannot just allow your flow of consciousness to bring you into whatever that happened to trigger your attention. You need to tell yourself, okay, now among all the tasks in my mind, the number one for me now is to finish this presentation, right? So that what's my step, or what I'm supposed to do in this process, I need to plan it for myself. In NARS, in a sense, we already have that mechanism in place. We have a bunch of mental operations which can allow the system, for example, to adjust its own resource allocation. Okay? Pay attention to one thing more than something else. And also, it can learn kind of like a meta-level skill, like how to write a paper or how to make a presentation. That kind of thing need to be learned from your experience, right? So then it becomes a sequence of mental operations that you can control yourself. And that mechanism is already there. We already allow this mental operation to do something, but it's far from well developed. Okay, we need to decide whether the current operations are enough. And also, especially, we need to decide when to use them. And we need to learn that kind of knowledge. I mean, NARS, okay, need to learn that. And we need to tell the system how to make that learning happen. Okay. So this is kind of like within the control aspects. But there are also some other things which is not literally within the control aspect, but still make a very important contribution or influence. One is the system configuration and the parameter setting. Like, for example, I already said, each memory space has a capacity. Recently, already some people suggest to me, NARS seems too random because maybe the buffers are too big. Buffers are large means that you will have multiple active tasks there to compete for resource, right? If you only allow 2 or 3 of the active tasks, the system will be more focused. That's for sure the case, okay? But whether that's what you want or not. You see clearly we have different configuration which will decide the initial value of the parameter. And the parameters, by the way, we call them personality parameter because very often it's not a matter of right or wrong. It just gave, for example, the logic part also have parameters that say inductive reasoning, how fast your your confidence level will increase with the increase of evidence. That's controlled by a parameter which is a well-known k value, right? There is no optimum value, but if you put a big value there, that means the system will, the confidence level will grow pretty slow. You need a lot of evidence to convince the system about something. On the other hand, if you make a smaller number, and then it will take action much faster given the same amount of evidence. So which one is better? There's no such a thing, it's just different personality, okay? And different value may work better in different environments, but since we're talking about AGI, there are many different environments, right? So that's something we still need a lot of work, okay? And altogether, you can say that's the innate aspect of the system. That's the nature, because this kind of thing, typically you cannot change it in the runtime without destroying the system's integrity. Okay. And also, finally, there is the issue of education, which is the nursery aspect, especially, for example, self-control knowledge. That typically comes from experience, not from built-in content. Okay, so the education, how to teach the system problem-solving skills, we haven't even touched it. Okay, only start to talk about this recently. And by the way, recently the Chinese team is working on this kind of thing. They train the same NARS with different input sequence, then try to see what happened to the conceptual network developed from it. At the very beginning, but this is an interesting direction. And finally, we talk about the evolution property, possibility of adjust the configuration and parameters from generation to generation. So in essence, we're talking about a species level adaptation, not an individual system level. All the other things we are talking about the individual system. My belief is if we want to fully solve the control mechanism, we probably need all of those. Okay, that is why I don't think just we don't want to blame all the problem to the body function. Currently, the current version doesn't run well, but just because, say, we don't have good body function, that's part of the story. Okay, it's not a complete story. So now you'll see that the control mechanism to actually make it work well, it's a very complicated task. But I think there is no way to avoid that. So my conclusion, the control mechanism of NARS is fundamentally different from the traditional one because, again, acre, right? You don't have the algorithm to follow, and you cannot do exhaustive search, then what else? So the objective, this is very important, is not to optimize performance on any problem, but to spend available resource in the kind of like most reasonable way. And you need to evaluate this according to the global evaluators and not its performance on one single thing. So I want to recommend you this, especially in the next stage when we are doing testings. You don't want to tune the system too much toward one specific task, unless we're talking about application. Application will be a different story, okay? You don't want it to be so general, you want it to work well one specific task, you don't care about the others that much. But in general, that's not the way to go. Another thing is also, I recently realized, previously I always have the dream or hope that the control mechanism will reach the same level as the logic part. It's kind of like relatively mature and well justified, and we can say this is the right way to do things. For the control part now, I more and more realize there's no such a thing as a single optimum control strategy. But on the other hand, it doesn't mean everything goes. It doesn't mean the current situation is good. Okay, so we still need to find the boundary of what we call a reasonable control mechanism, and then we will allow different personalities to coexist in that. And then maybe in the future, we can put a team of NARS with different personality to compensate each other, as I point out in the roadmap we discussed before. But that's beyond the control mechanism. The most important reference will be my first book, and actually not the second one. The more recent book is more focused on the logic part. Okay, the first book is more balanced between the two. And also the technical report we just finished, which include a lot of unfinished work, okay, on the control mechanism. But that gave you the overall picture. So that's all.